Okay, so moving on quite quickly. Next, we have Dr. Dai Yamamoto from TOSHIBA Corporation. He acquired his PhD in chemistry at the Tokyo Metropolitan University, and Dr. Yamamoto joined TOSHIBA Corporation for material research and cell development on lithium-ion batteries. He's currently head of the product business development team within the battery division, promoting its NTO product, niobium T being, I believe, TI titanium in this case, which he will now explain in more detail. Thank you, Yamamoto.
Okay, thank you for introduction, and I'm glad to join this conference, and thank you for the CBMM. I'm Dai Yamamoto from TOSHIBA Corporation, and in charge of the production development of now niobium titanium oxide anode batteries. So today I will introduce the feature and the benefit for the application by using of the NTO, niobium titanium oxide battery anode. Okay, this is the outline of my talk. I will introduce our battery company vision and the feature of the anode material and the benefit for the application. And I will summarize and I will share the current status of the commercialization of these batteries. Okay, at first I will introduce our company vision. TOSHIBA Group formulated the environmental future vision 2050. It's a very, very long-term vision. In response to the recent severe environmental problems. So our TOSHIBA Group promotes to the development of the many products that contribute to the reduction of the environmental impact. Rechargeable lithium-ion battery is the one of the key products, and we are producing this battery since 2008. And in this situation, the electrification of various fields is accelerated, and especially the transportation field is remarkable due to the very, very important factor to realize decarbonized society. And the battery, which can store the energy from generation to application directly, is essential devices. And high performance battery is always required in this field. So the next topic is what is the advantage of niobium titanium oxide batteries? So at first, since 2008, we have been produced the lithium-ion battery we call CIB, which uses the lithium titanium oxide in its anode. By using LTO anode, the battery has many advantages, such as safety, low temperature operation, high power, and rapid charging, and long life performances. However, the lack of the energy density is the biggest disadvantage. This is for this battery. So our challenge is to enhance the battery energy density, mainly depending on the anode material. So we select the niobium titanium oxide anode. What is the NTO? NTO is the one of the metal oxide anode, and of course it can use as an anode material like LTO. The main feature of the NTO is energy density. It's high. It has a very high energy density compared to the LTO, and the volume energy density is higher than that of the graphite anode. Because it has the unique redox couple of the niobium and the titanium. So if the battery use the LTO, it's an anode, the energy density will be improved. The next point is the fast charging. The fast charging performance is the one of the main characteristics of the LTO batteries. But LTO battery can inherit that performances. The reason why is the difference of the reaction potential. NTO's reaction potential is close to the LTO, and it's much nobler than that of the carbon graphite and the lithium metal reaction. So the potential gap protect the anode from lithium dendrite deposition in charging situation, especially the fast charging and the low temperature charging. So the battery using NTO anode can show the high energy density and fast charge acceptance. This table compares the performances of each battery chemistry. These data based on some of the experimental data. And in this point, the energy density of NTO battery can improve by approximately 1.5 larger than that of the LDO batteries. And it is equal to sometimes higher than that of the LFP carbon chemistry. And these performance, NTO battery can inherit this rapid charging input power, output power performance from the LTO. Unfortunately, the cycle performance is slightly less good than that of the LTO, but we think it is still enough high performance compared to the LFP and any of the applications. So initial cost is now we are making the new batteries, but these performances can reduce the total cost of ownership and the system level of the cost. So totally, the NTO batteries performance is a very good balance, especially for the high fast charging applications. And we are already successfully prepare the prototype large size of NTO batteries. This is the specification of the prototype cell, and it shows up to 57 ampere hour, and the energy density is 330 watt per liter. This is much higher than that of the current conventional batteries. And it performed as well as in terms of the capacity and the quick charging performance and input and high output power. So this prototype cell shows the data based on the concept of the NTO chemistries. And this is a safety test result of NTO prototype cell. Even it has high energy, high ampere hour, more than 50 ampere hour, and it contained high nickel content. We could obtain no fire and no smoke and no temperature rising within these nail penetration test and bar crushing test. So this means the NTO battery we prepared has extreme strength to the internal short circuit situation. This is just information of our experience. LFP is also a safety battery in general, but at the end of life, we can see the many of lithium dendrite on the anode in this case. This is due to because maybe this is generated by the charging situation, and sometimes it becomes a trigger of internal short circuit and thermal runaway. So the charging condition of the LFP battery will be limited carefully. And NTO battery doesn't have these mechanisms of the lithium deposition. So we think these high level of the safety will maintain through the end of the battery life. Okay, so the next topic is what is the benefit for the application by using NTO batteries. So up to now, we are making the SCIB battery, and this battery has applied to many of various applications. And taking the advantage of high input power and fast charging. So many of the application, improving the efficiency in operation. And more, there is no restriction of the charging. For example, so fast charging and the low temperature charging. So and the high level of safety of the battery makes it useful for many of application operation. And of course, NTO battery can take over the benefit for the application. And improving the energy density enhance the functionality of many of applications. So the one of promising the new application for the NTO batteries EVs. Actually, LTO battery has many of advantages, and it's making the useful for the EV. But the lack of energy density is critical, so it cannot be a candidate for the EV application. But improving energy density by LTO can improve the drive length comparable to the LFP battery chemistry within with the very short fast charging within about 10 minutes. And other performance makes it useful for the many of the EVs. For example, this is the power data of our prototype cell. This is output power and input power. It shows very high level of the through the wide SOC range. It can be indicated that the high acceleration can be demonstrated for a long time in any charging stage of any state of charging. And also, you can charge fast charging for any SOC condition. And so the NTO battery can make it useful for the future EV conditions. So it is very good useful for the industrial mobility like buses and ships. And we are making the battery, is LTO battery to the fast charging EV bus, for example. The fast charging EV bus, which required less capacity of the battery, can improve the bus weight and bus space and of course cost. But low battery capacity is means the very short drive length per one charge. It will be limited. It will be limit the route and operation plan of the EV bus, and which short drive length needs a number of fast charging stations. So it improved the investment cost. So if we can use NTO battery, the drive length will be improved. The long drive range reduce the fast charging station. So the capital investment will be improved with NTO batteries. Of course, it is the same situation for the logistics and delivery systems. And in these electrification applications, the high energy density and the fast charge acceptance battery is always needed to reduce the CO2 emissions and automatic operations. So improving energy density is can reduce the size of the battery. So many of small applications like a bike, AGV, and AMR and drone can equip the fast charging performance with NTO battery. It can change the efficiency of the warehouse operation and delivery. So as we discussed above, the high energy density and fast charge acceptance will change the many of the efficiency of the application within. Okay, so I'll summarize my talk. Okay, so the NTO battery can revolutionize the electrification applications. So far, LTO battery can achieve the fast charging acceptance, but it sacrifices some of the energy density. The NTO enable the coexistence of these performances, like charging energy density and high fast charging. So the high performance electrical application will be realized with NTO battery, like the sports type EV or heavy industry, like working in the mine and the construction site, and more effective transportation. Okay, so the summary of my talk. The NTO anode materials has double of the volumetric capacity of graphite, which is a promising candidate for alternative anode to LTO. The prototype LTO cells shows about 1.5 or more higher energy density than that of LTO. It still has rapid charge acceptance, long life performance, and safety. And these new high energy density battery containing niobium makes it possible to expand the cruising range of EV compared to the chemistry with short charging time within the 10 minutes. It makes many advantages for the commercial and future EVs. This is the final slide of my talk. I will introduce our commercial plan of niobium batteries. This is the spec of the battery, which we are working on the commercialization. Now we are making the pouch type niobium titanium oxide cells, which has about 50 ampere hour. And the energy density is about 350 watt per liter. And of course, it can charge 10 minutes for 5 to 80% of SOC. Now we are verifying the design and process and the quality. And I hope I'd like to deliver this cell in early of 2024. Okay, that's all my presentation. Thank you for your attention.
We'll have some questions at the end if you'll still be around. Thank you. I think for me, it just goes to show once again that battery technologies, it's always dependent on the application. Applications, all very different technologies have their pros and cons in different cases. Thank you for that, Dr. Yamamoto. So next we have Dr. Oliver Osters from Skeleton Technologies in Germany. Oliver is VP of Technology at Skeleton. He's a chemist holding a PhD from the Technical University of Munich. I think you were there at a different time than Rahul, though, not at the same time exactly. Strong background in solid state and electrochemistry, working from 2012 and between 2012 and 2022 on the development and industrialization of lithium-ion batteries for Mercedes-Benz and later Volkswagen. At Skeleton, he is focusing with his team on the scale-up of next-generation supercapacitors using curved graphene and the industrialization of the super battery. So, Dr. Osters, over to you.
Thank you very much. Also for you guys having me here and giving me the opportunity to give you a kind of introduction about, let's say, also what Skeleton is. I think I had quite a couple discussions already with questions who we are, where we are from. What I'm going to give you today is a short introduction to our super battery technology, especially for fast charging applications, but also especially on our vision of the market, where I want to thank you, Ian, for the introduction, especially application-driven approaches. What do we need for which application and where to tick the boxes for different different customers. So let me start. So we at Skeleton, we have the vision and also the mantra to fight the climate change. And that's actually what drives us every day. And to achieve or to be successful on this mission, it's quite obvious we need electrification and zero emission technologies. And to enable this, we need energy storage. So we heard already a lot today about energy storage, and so also let's say one can say lithium-ion batteries are actually a very good way to address this issue. However, lithium-ion batteries do not fit all solutions, and that's where we as Skeleton come into the game, and where I'm going to give you kind of short company intro. So actually, Skeleton was found more or less in a garage back in 2009 by 3-4 people having the idea to commercialize a new material for supercaps, and actually they succeeded up to date. And we are already operating the largest and most modern factory in Europe based on supercapacitors, which is based in Groß-Röhrsdorf near Dresden, where we are producing on industrial scale around 300,000 supercapacitors a year. We have also our supercapacitor research and development center over there. However, it's not the only way or the only location. We have Bitterfeld-Wolfen, where we have our material research, which is also one of our cores of our strategy, that we cover the whole supply chain. We have another, let's say, our software and electronics development in Tallinn. And we opened also in Berlin an office for sales and application engineering and grant and IP management. So latest news, we also added now Markranstädt, which is near Leipzig, where we will open our new supercapacitor factory in the beginning of 2024. Where we will have a fully automated supercapacitor production line, enabling us to produce 40 times the volume we can produce today. So what makes us, let's say, in my opinion, also different, and what made me also, let's say, change from large corporate to Skeleton? I think pretty unique. We are really covering the whole supply chain from material to single cells, industrial modules, and systems. So based on our core material, the curved graphene, we have several products on the market. But let's say our customers are barely requesting cells. So some are requesting cells, most of them are requesting industrial modules, but also many of them are requesting full systems covering then or being then really turnkey solutions on the grid. So what's the difference between our core technology, supercapacitors, and lithium-ion batteries? So supercapacitors, of course, have a super high power density, up to 60 kilowatt per kilogram. They have an extreme cycle life, so you can charge them almost infinitely. They have extreme fast charge rates, about 2000 C. They are inherent safe, easily recyclable, and especially in supercaps, the only metal we have in there is aluminum. Of course, it's not all light. There's also some shadow with every technology. The limited energy density compared to lithium-ion batteries makes it, let's say, at least not usable for traction batteries or wherever where you have huge energy demands. And this is where we are then also focusing now in the future. So our core products we are selling right now in 4 different segments. So we have automotive, transportation, heavy equipment, grid renewables, and industrial applications. So for automotive, it's of course not traction batteries, that's for sure, but let's say the supercapacitors are a very good addition to fuel cell electric vehicles. We all know that fuel cells are still suffering from, let's say, especially spontaneous peak loads, whereas the supercapacitors can be a perfect addition. We have our product in the market for 48-volt active suspensions for curves in automotive as well, and of course for board net stabilization. And one of the newer applications as well is safe stop applications. Automotive is changing to steer by wire. In this case, if you have an electric vehicle and the battery has whatever, like some runaway or so, you need to be able to stop the vehicle safely, and there the supercap is a perfect vehicle. Then we have the transportation and rail, where we are also using curves, especially for reducing the energy consumption. Actually, we can reduce the CO2 consumption by 30% actually by using such railways, also in trams. We have in the heavy equipment the engine start function, also let's say one of our core products, which enables truck drivers to reduce the downtime, even especially when you look to North America, you have cold winters. Battery is getting low overnight. Our product is able to get so much energy out of an empty lead acid battery so that you can still start the engine. Then, in addition, we have grid and renewables, especially in wind turbines. Almost so we are using our supercapacitors in the pitch control, especially when you need to turn the blades in the wind. Currently, you use lead acid. Supercapacitors are much more efficient, less of maintenance. Therefore, a very good idea. And of course, when it comes to grid and renewables, we are working on large systems which can apply up to 50 megawatts for 15 to 30 seconds, which is actually the perfect use case for supercapacitors. And last but not least, industrial. We are working also in intralogistics, working in curves also for port cranes, forklifts, elevators. Yes, and of course, fast charging applications where we just need a short power time. But if we compare the different technologies again, so we heard already today something about high energy batteries. So where we have, let's say, a huge amount of energy, we have, I think it's a point we can argue. We saw the power is really that low for conventional lithium-ion batteries. If we compare it to supercaps, I think it's a valid point. We have issues with safety. Resources are, let's say, at least questionable. However, lithium-ion batteries are profiting from the scale and especially from the energy. In between, we have the high power batteries, which are very safe, have a good power, energy, scale, and also resources. Let's say they are somehow a very good intermediate in between supercaps and high energy batteries. And then we have the supercaps, let's say, where we have incredible power, inherent safety, very good availability of resources. Yes, we as Skeleton are working, of course, on the scale. And where we are talking about today is then also the energy. So to give you a kind of introduction to our roadmap. So actually, we introduced our generation 1 supercapacitors in 2017. But based on our, let's say, core of the material development, we are working currently on 2 new generations. One is a graphene-based supercapacitor, applying our curved graphene, which has an up to 70%, slightly higher than 70% increased energy density to compare to today's supercapacitors, while remaining all the good properties of the Gen 1 supercap. And what we are working on right now is, let's say, also a new material concept we have developed during the past years, which ends up in our super battery. The super battery has an increased energy density up to 65 watt-hours per kilogram. We have an incredible lifetime for this concept of 50,000 cycles. We can charge in 60 seconds. We have an extreme competitive cost base. Because we can, on the one hand, set up on available materials, and we are not dependent on materials like cobalt. Of course, and what I will show you now later on is also we have a extreme high safety in these cells. So to give you a kind of introduction, so what are the materials we are using? So we are focusing still on the form factors we are using also in supercapacitors. So our main product will be a so-called D60 cell with a diameter of 60 millimeter and a height of 138 millimeter. Cylindrical cell, so relatively easy to produce. So that's what we are doing. We are using, let's say, 32% organic components. We have aluminium as a main material, nothing else. So we have other materials, but let's say no copper and nickel and cobalt. So to give you some more insight of the specs, so we have a voltage window from 1 to 3 volt. Within this we can apply 65 watt-hours per kilogram on energy density. The operation range is from -30 to +50 degrees C. And from power perspective, we can achieve 10 kilowatt per kilogram from 10 to 50 degrees C. At lower temperatures, of course, we need also derating. From safety perspective, it's quite impressive. We made several tests like crushing, overcharging, overheating, and nail penetration. Actually, it happens nothing. Even if you crush the cell like this, of course, we have leakage because the cell is not mechanical integer anymore, but there is no fire, no explosion, no nothing. Also for overcharging and overheating, nothing critical happens. And even the nail penetrating through the whole cell with a 3 millimeter nail is causing not a problem at all. But coming more to the application point of view, which I told you I will talk about a bit in the very beginning. There are actually 3 different power requirements which are sometimes coming along together, but sometimes also contradicting. So we have on the one hand the fast charging, which is especially important when it comes to high utilization, and you have let's say no charging storage which is in between. Then you have the high power discharge, where you need, let's say, in certain applications, very high power at a certain point, but you are not so much dependent on the charging rate itself. And of course, you have the third part, which requests a high RMS current, where especially the lifetime is dependent on the power density and the ESR. Independent from these power requirements, there are not really new, but let's say upcoming requirements which are getting more and more important, either by legislation or also by customer requirements, which is on the one hand safety, so that you need less overhead. Let's say if we talk about automotive customers, nowadays it's still a big topic to prevent and, let's say, define measures against thermal propagation of the battery, which is quite cost intensive, and this is in this area one of the important points. On the other hand, you have the sustainability. You need to be aware that you have clear, or that you know your emission footprint, that it's as low as possible, and that you have the total cost of ownership covered, and in best case also the end of life cost, considering a circular economy. Then you have the supply chain security, where you of course want to have on the one hand a stable supply of your materials, but also to a stable price, and that's where it comes along. Again, you might say lithium-ion batteries might be a very good fit. However, and I would agree for many use cases, to be honest. But in the end, it's also about the price. If we, for example, consider fast charging, high RMS currents, power discharge, and high RMS, you can achieve all with a lithium-ion battery, of course. But in the end, it's a question of oversizing. And if you think about oversizing, the commercial part comes into game. So, for example, if you need a 400 kilowatt hour battery at a price of 100 kilowatt euro per kilowatt hour, it's actually a cheaper solution than a 100 kilowatt hour battery. Use a high power battery with 100 kilowatt at a price of 500 euro per kilowatt hour. But in the end, this is the gap in the oversizing where you need to find the right balance for the application. And I'm going to show you on the next slides what's our view on this in the future. However, before I come to that, I want to give let's say a short intro also about the three requirements: safety, sustainability, and supply chain risk. So I don't want to be the bad guy and say lithium-ion batteries are unsafe. That's definitely not my intention. However, still, let's say the cells and also the systems are suffering from accidents, from, let's say, quality issues, whatever, which cannot be excluded by 100%. So still, we see fires, we see, let's say, especially when it comes to critical infrastructure, incidents which are critical for us and also for the operation. From sustainability point of view, I think we heard already about cobalt quite a lot today, so I will not go into this topic again. But also from supply chain risk, even if we do not consider cobalt as a critical element, or copper or whatever, but if we talk about even about nickel, I brought here the price fluctuations from 2018 to 2022, and it's quite significant. And this is everything else but a stable supply chain. And this is what you need to consider when we are talking about different applications. So the first application I want to explain to you here is actually a data center, UPS. So in uninterruptible power supply solution, actually they need high power discharge only once for a certain point. They need extreme high safety because actually if something happens in their data center, it's quite expensive, and let's say the impact might be rather high. They have a sustainability approach. And if you consider all the different requirements they have, so like having a very high power profile for 15 to 30 minutes before the gensets or fuel cells set in. So you need a very stable and reliable solution. Best case without maintenance, where you could also think about lead acid batteries. So, and if you tick all the different boxes for the design of such a system, actually, actually, the high power LTO cell would be a very good fit, and there's not much more to say like this. The other solution, I just got to notice that I have 2 minutes, so I will speed up a little bit, is actually the mining truck solution. And there comes our super battery technology in. So mining trucks providers or operators need ultra fast charging. They need high safety, sustainability, and of course a very stable supply chain. Because if you think about prices, also in this case, if you compare a system and you would oversize something like this here for a mining truck as a standard conventional lithium-ion battery system, the cost of one energy storage would be around 1 million. For our super battery, it's 400,000. And actually you can charge it in 60 seconds, which means during dumping or loading of new material. And actually, therefore, it's a perfect fit. So I'm jumping over this a little bit. Sorry for this. Actually, it's our this is actually where we also are in the same project like Echion, also in the charge on. So this is where we are working on. Yeah. Just going through it, let's say the main benefit for the super battery is, let's say, we have a fast charging as the default option, no plating, no nothing. We have an increased efficiency for the full electrification. We can lower the peak demand on the grid if we apply also the additional backup storage. And actually, the solution is applicable for all machines depending on a high utilization. We have mapped out several applications categories. I will not go into detail for this. And then also maybe skip the conclusion for now. It's in the slide deck. I would thank you very much for your time listening to me.
Thank you for closing out there as well.
Yeah.
Conscious of time, we have Anna coming on in a moment. We have a tea break a bit later. I'm trying to make sure we have time for questions and still the tea break. So very interesting. I notice in that kind of application, people are often hybridizing supercaps, or I also hear the word supercap batteries these days. So I don't really know where that's come from. Oliver, maybe. Yeah. Yeah. Okay. Thank you. Okay, so next we have Dr. Anna Wise from Nyobolt. Anna's going to be talking about the niobium tungsten oxide technology. Anna's head of strategic programs at Nyobolt. Prior to joining Nyobolt, Anna held the role of head of battery technology at Innovate UK, where she led the innovation programme and technical direction of UK government's £330 million Faraday battery challenge. So she's pretty well familiar with where I work these days as well. Thanks for that, Anna. She's an experienced chemist with a PhD in electrochemistry. She previously worked at Stanford University and the SLAC National Accelerator Lab in the US, carrying out collaborative research with businesses and academia on battery materials. Anna, over to you.
Thanks very much, Ian, and thank you very much for the invitation to present to you this afternoon. So yeah, I will be talking about Nyobolt's NWO technology and the applications in which it can be used. But I'm going to start with stepping back a bit and talking about how this actually works, where it comes from, and then how we actually get into the application. So long life, high power and fast charging, all in the same battery. So Nyobolt's technology can do this. So it's a combination of that fast charge and high power with the cycle life, with compelling energy density and improved safety. So a cost competitive solution. But traditionally, when we think about lithium-ion batteries, we think potentially, if you hear fast charging, high power, and long life in the same sentence, you don't typically think that they fit together. We normally see degradation linked to fast charging or high power applications. So if you're moving electrons and ions around, trying to move them quickly, then things can get hot. And this triggers a myriad of degradation mechanisms. So we talked a bit about the cathode this morning. We heard about the cathode reactivity, especially as we're moving to higher nickel materials. And on the anode, we get this breakdown of the passivation layers, increase in the SEI, and an increase in the resistance. So if we think about how we can address this and enable that fast charging, on the cathode side, again, had a great discussion on this morning. But as we move lithium ions in and out of the cathode, we see this changing in the spacing of the layers. And there are routes to optimize this, some of which we heard this morning. So there's excellent work happening in those areas, but around the morphology, around doping, coatings, and the particle size. But if we look at the anode, so typical materials such as graphite shown here, as we charge the battery, the lithium ions move into the structure. And as we charge more quickly, they build up on the surface, we get plating, and this can form dendrites on the surface, which can, as it builds up, penetrate through to the cathode, get short circuit, thermal runaway, not a happy battery. So we're limited on charging times by this phenomenon. So Claire, Kent and others in Claire's research group have done a huge amount of work looking at finding a new material that enables fast charging from the anode perspective. So really looking at anode, or looking for an anode material that operates at a higher voltage than 0 volts, so avoiding that lithium ion plating, and has high lithium ion mobility. So an example of a structure looked at as a perovskite structure, where the lithium ions can jump into the different channels. But as you start to fill up the structure, then you get distortion, and you end up with the ions essentially getting stuck. So really what Claire and Kent, and it's a bit strange describing Claire's work when she's sat in front of me, but I'll keep going. But yes, so looked at how could design optimum structures, so materials with pillars that can prevent this disordering and the ions getting stuck. So looked at these shear structures where you end up with these pillars that can prevent that disordering, and also the block structures. So again, looking at really stabilizing that structure with the insertion of lithium ions and enabling that movement in and out as it's going. So Claire obviously showed this slide earlier, but Kent in Claire's research group and others screened a large number of tungsten and titanium substituted niobates, looking at the structures, looking at fast lithium ion transport. And one of the structures that was developed was the niobium tungsten oxide 16555 structure. And this really did demonstrate that high rate capability, so fast charging. So a 3-minute charge demonstrated in this material. Looking at how that maintained over cycles, so in the research work, so seeing 500 cycles with a 12-minute charge and discharge, and this is all reported in the Nature paper published in 2018. So obviously we know Claire and her group do a lot of NMR, so employed this technique to try and understand how we can or understand exactly what's happening with that lithium ion diffusion. And really what was seen was that you can essentially in 3 minutes a lithium ion can travel 33 microns through an NWO particle. So that's pretty impressive. And it means that you don't necessarily need to worry about having a small particle while maintaining a fast charge. So that lithium ion diffusion, that fast diffusion through the particle really does enable you to have that fast charge without losing the cycle life. So fast lithium ion diffusion, long life, high power, and fast charging in the same battery. So Nyobolt was founded to commercialize this technology, and so I'll talk now about how we are taking that to market. So we're really building on this work to deliver fast charging products to our customers. We've grown significantly since 2019. We now have a team of over 60 worldwide. So we've got teams in the UK, in the US, in Boston, and in Asia. And we're very lucky as well to have global experts on board leading those teams. So we've got very strong expertise in different areas required for the commercialization of lithium-ion batteries. We had a successful Series B raise this summer, so raised £50 million, and that is enabling us or starting us on that journey for that scale production. And that's really where we're focused at the moment, is ramping up the production to meet the demand of our customers. So in terms of where the technology sits, so we've got obviously the, oh god, no, that's not what I wanted. I thought that was a pointer, but it's not. All right, so we've got obviously the proprietary metal oxide anode material, so the NWO. Everybody recognise those block structures from the papers. And we're also working as well on combining that with BMS and battery management, sorry, the systems integration side of it, to really get the optimum out of that technology. We're format agnostic, but everything is optimized for high power. So we're using commercially available separators, electrolytes, cathodes, again, all optimized, screened, selected, optimized for high power, and working with partners as well to develop those. So I touched on this. We've obviously started with the anode materials, and we do the R&D and manufacturing in-house. we have a very experienced cell engineering team based in the States. And there we've been able to really accelerate the prototyping and development of cells in different formats and optimizing the performance of the cell as a whole. On the pack side, again, we've got an excellent team of engineers based here in Cambridge and really looking at how we, putting together packs for different systems, the control systems around it. And we're also looking at how we looking at the charging side of it as well. So really being able to leverage expertise across the materials to the systems to be able to deliver that optimum performance to our customers. In terms of how we're getting there, where we've got to so far. So I think, it was 2020 we made the first ton of the material. So scaling since then on the ton, multi-ton production of the niobium tungsten oxide material. We're currently building a pilot facility for hundreds of megawatt hours equivalent production just outside Cambridge, and looking obviously to increase that production of powder in the future. On the cell side, we've been able to do a huge amount. We're using industrial scale pilot facilities. So these are pictures of some of the facilities that we've been using in the US to really coat hundreds of meters of electrodes and put together multi-layer cells. We also have a partnership with Coventry University, and Alex there has been producing 21700 cells for us. And through the access to the facilities and the team that we have on the cell design, we've been able to really get going with those industrial cells, and we're ramping up production at the moment with partners. So what that then translates to in a cell, so we've seen some plots like this or along these lines already today, but obviously if we're comparing the input power density of different technologies and the energy density, we can see that with our technology, we're able to achieve extremely high power density performance, but combined with energy density that's comparable with high power lithium ion cells. So it really is addressing a sweet spot in the technology, or sort of in the performance space, where you can achieve that fast charge, but you have enough energy to do what it is that you need to do. So combining that, though, with the long cycle life gives you an attractive proposition for many applications. And a few of those have been mentioned already. So we see this as really meeting unmet needs. So there are many markets where you want that combination of fast charge, long cycle life, decent energy density, because it enables productivity, it enables high uptime, it enables you to size your battery appropriately, to use the appropriate level of resource, both in terms of the materials that you're putting into the battery and the resource required to make them. So we're working in a variety of sectors, and there are some examples here. So on the EV side, obviously, fast charge is attractive to customers. You can have a smaller battery in your vehicle and still have suitable range. And then if you're looking sort of all the way on the EV spectrum, the high performance side of it is an area where, they want the high power out, not just the high power in. If we're looking at industry and automation, and also the heavy industry, it's around, the total cost of ownership and really being able to have maximum efficiency in running these sites. And cordless tools, again, it's an example of high power out, also needing high power in. So there's a variety of applications. I mean, Jean talked through some of the market space where the fast charging, high power and long life is needed. And there's a huge opportunity for commercialization in these areas and huge customer demand. So the key thing for us that we're really focusing right now, as I said, is scaling to meet that demand. And that's a fun challenge to have and one that we're sort of grasping with both hands. And yeah, looking forward to share more as we continue to grow and scale. So thank you very much for your attention. If you have any questions, feel free to get in touch. But yeah, thank you.
Thank you very much, Anna. You brought us back almost on schedule. That's brilliant. Thank you. That was ladies and gentlemen, would you like to come back up on stage for a quick questions and answer session? Those of you that have just spoken. So we've still got Rahul's gone now, I think, hasn't he? But yeah, Oliver, Anna, would you like to come back up? Dai, if you'd like to. Thank you. So we had a little bit of time ready. We had tea break at 3:25. We started 10 minutes late on this session, and we're now only running about 15 minutes late. So it's up to you guys, really, how many questions you've got. Got a good panel here. So we got a microphone available. So first, who's got the first question for us? One over at the back there. Thank you.
Oh, hi. So my name's Jawad from UCL. Thank you for the nice talks. I think Stanley Whittingham earlier talked about continuous manufacturing, which is something I'm a big believer in. Continuous manufacturing, and that this was a really important issue. And of course, thanks to the energy crisis, we're all worried about energy costs and manufacturing and low energy manufacturing. So the question is, what are you doing related to improving product quality and consistency when you're scaling up? And are you looking at low energy manufacturing or more efficient manufacturing for lower environmental footprint?
Is that a question primarily aimed at the materials themselves, or the cell, or the whole process?
It's purely aimed at scale up and material scale up in particular, yeah.
Okay, so materials. Maybe Jean, is that a good one for you to start with?
Yeah, is Alex in the room? Yeah, maybe Alex can take this one.
I thought I got out of it, sorry. So the answer is yes, we're looking for materials manufacturing scale up at continuous manufacturing processes for the increase in productivity and saving on energy. So with batch processes, typically in battery materials, there's a lot of heating up and cooling down. And if you have to do that all the time, it's a huge waste of energy, although it's easier. So that's yeah, we're focusing on that as we go
on. I'd say as well, the location of where your manufacturing happens is a key factor, of course, in the energy consumption and how clean that energy is. That's something we're looking at as well.
No. Okay. Comfortable with that? Okay, thank you. Can we have another question then, please?
So Lubna from Echion Technology. So thank you very much for this excellent presentation you have done. So I have a question for Dr. Dai from TOSHIBA. So we have seen TOSHIBA a long time ago working on prismatic cells. Why you are moving to pouch cells for TNO product?
So we don't have limit the shape of the battery. So we make the prismatics and the pouch and cylindrical for adapt to any applications. So now in this presentation, we are making the pouch type cell. We aim to increase energy density. It is our first priority to make the NTO type battery cell, but it is still have some high power charging acceptance. It is we designed a high energy density and hard charge acceptance. So the pouch is a good shape of, and we can make the large type of cell easily. So we select the pouch type in this type. Right.
Thank you very much.
Do you have any more? Okay.
Hi, this is a question for the Skeleton Technologies. So when you short circuit a supercap, it's a pretty rapid response. So I was interested in the nail test, why there were no problems in that, and then following along, what's the electrolyte you're using? I mean, are there issues heating and that.
So for supercapacitors, I can definitely tell you. For super battery, I cannot disclose at the moment. For supercapacitors, we are using acetonitrile.
That's still on the roadmap for industry, acetonitrile.
We are changing, let's say, the salts
Yeah.
to achieve higher voltages. But let's say from the liquid, it's basically acetonitrile.
And when you put a nail through that, there's no heating and evaporating. It's all okay. And in terms of the materials, do you your material space, do you think there's much room for innovation beyond just a carbon from a coconut?
That's the reason why we developed the super battery.
Yeah.
Because with solely physical storage, we are at, I would
so
say
you have a
we
little
are
bit of a Faradaic component in it.
Sorry?
There's a Faradaic component.
Yes, exactly. So with our supercapacitors, it's really just Faradaic storage.
Yeah.
And with the surfaces we achieve with our curved graphene,
But it
also
must
what
be
we know from the market,
graphene.
it's
Curved graphene plus.
Yeah.
Then. Thank you.
Wondering how will the future EU battery normative or the Inflation Reduction Act in the US is actually affecting your plans and strategies as companies?
I think I think there's two sides to these questions. I think on the maybe more constraining side of things, there's a set of regulations that the whole industry needs to comply with that comes with these measures, and it's a good thing. I'm not complaining, but what I have in mind in particular on the material side of things is really understanding the life cycle analysis of the material, having strategies for recycling. So that's a whole host of things that need to be looked at and prepared for well in advance. So our approach on that at Echion is to partner, and we're working with the University of Ghent, for instance, on life cycle analysis. On the plus side of things, I was in Detroit, no, in Washington, sorry, Washington DC, when the Inflation Reduction Act was announced, and I think the energy in the room, it was a battery even, the energy in the room was fantastic, thanks to that, and I think it's really energizing the whole industry in the US, and you see. I was just looking earlier on my phone. Microvast is announcing a 1 gigawatt-hour project, and all of this, and you have an announcement like this twice a week since this happened. So yeah, fantastic energy in the value chain, and our strategy at Echion is to, of course, capitalize on this and get in early with the new projects that are starting. And for us, that means increasing our presence in the United States, which is basically opening an entity there, which is what we're doing.
I would also say for skeleton technology, it's more like a chance. So for life cycle assessment and let's say the European battery regulation, I would say it's not so much affecting our business right now, because most of the things we have been working on, because it does not make sense to bring an unsustainable product to the market as of today. For let's say the changes in the US, this is for us a chance to maybe prepone some of the plans which were on the long run, but no decisions yet from our side.
We think the safety fast charging system is a key point. This is it can reduce the total amount of the battery. In this space, there are many battery, many amount of batteries, and it will become the waste. So to this situation, the regulation is more restricted. So we have to change the total amount of the battery by using of the fast charging and long life performances. So we are saying whole single things. So we the next generation's battery needs the fast charging and long life. This is the new value of the battery society. We think so.
I think we've always been focused on a sustainable approach and really making sure that we have sustainable supply chains in place that would then, obviously comply with the European directives. And the IRA, I mean, there's opportunities there. Is also, it gives is a good point to have a look at the global market and the changes and the shifts. There's a lot of things happening, and yeah, most of them opportunities. So, but yeah, the sustainability is key, and we're very much focused on that. So.
Okay, probably got time for one more question if we want to have a tea break.
It's good to see you all together. Robson from CBMM. My question is, of course, most of the applications are very similar to the technology. When you look at the passenger vehicles, EVs, which is the biggest market so far, what's your view? What is necessary to do with Niobium, whatever the technology you guys exploit to get to this market? What is next?
No, I think yes. Passenger cars are seen by many as the holy grail because it's a gigantic market. I don't think it's a good route to market for companies like Echion. I think one thing I really like about the applications that we target is that they're really driven by total cost of ownership, which means that there is not a lot of room, but a bit of room for the initial cost to be higher. So that means margins that are more sustainable for the whole supply chain, not only the vehicle integrator, but also the battery manufacturer, the cell manufacturer, and the material production. And I think that's needed to penetrate the market. You don't need to reach CATL scale to have a business, and that's very good. So I think it's a necessary step forward to go there. Then will we ever go to the passenger car market? I think for us that's our XN05, which is more of a concept, a moonshot, if you like. So it's all about increasing energy density, decreasing cost, as in dollar per kilowatt hour cost drastically. So I'm sorry, that probably means less niobium in it.
Well, from our side at the moment, we are not targeting passenger vehicle market. I think Jean is completely right. You need to focus on energy density in the end. Just having the fast charging time is not the key. It's in the end then balancing even more like.
So the variety of the EV will be enhanced for the future. So mainly the commercial EVs and the mini size and the large size and the bus, so something. We think so. Same. That not only the energy density is important. It's balance of the battery performances like cycle life and the safety and quick charge and the energy density also, of course. It is the balance is important for the variation of the EV expansion, I think.
We're already seeing segmentation in the EV market in terms of batteries that are being used, and the sizes, the shapes, the properties of those batteries, and what customers are looking for different use cases. So I'd say that there's definitely potential for that to segment further. And there is an opportunity with these batteries to target a smaller battery that can charge quickly, which would be suited for urban environments, short journeys, people that don't do a high daily mileage. It's unlikely to be the solution for every vehicle, but yes, I can see some segmentation there. But there are also enormous markets outside of EVs as well. So targeting passenger EVs, where it's really about that long range and costs down, the longer range vehicles, it's not, we don't necessarily view that as a sensible target.
Okay, so I think, okay, one very last one then.
So thank you for the excellent session that we have here, but just a question. So in order to have fast charging, battery is one part of the problem. So we need to rely also in infrastructure. How do you see the infrastructure coming, at least in Europe, USA, and Asia, in terms of more capability to charge? Any comment on that?
If we're talking about EVs, obviously we're seeing a rollout of higher powered chargers. But if you've got a 100+ kilowatt-hour battery, then that you want to charge in just a few minutes, then you'll need a much higher power charger for that than is currently being implemented. Again, that comes into, does it make sense to have a smaller battery in the vehicle? So there's an opportunity there. And then, I mean, looking at applications outside of EV, we're seeing reports of multiple megawatt chargers for industrial applications that are being developed. And then if we're looking at the smaller end, there's improvements in the power electronics all the time to enable that. So I'd say, yeah, the infrastructure is improving, but for certain applications, you really need to consider the whole system.
Yeah, and I think for us, we really see also, let's say, not so much for the automotive infrastructure, but especially also during mining, in the mining truck applications, we are actually working on multi-megawatt really megawatt storages to buffer and to have the time in between when the battery is not used, because otherwise the grids will collapse. That's I think the main thing we have to think to the end, that we have also storages, let's say, on the one hand in the industrial engineering, in industrial applications, but also, let's say, if we talk about highway charging stations, it will also come to such solutions.